Okay, so welcome back to ChemPrep Hub. I hope your IIT JAM preparation is going well. So we are back with another good question. This is basically MSQ type from JAM 2024. This is a JAM 2024 question and it's again an MSQ type. Okay, so it has asked that the suitable synthetic routes for the following transformation are. So, as you know, MSQ requires the approach that you have to go option by option, treat every option as a separate question. Okay. So let's start. So we'll look at the first one. So it says para-toluene sulfonyl chloride, and that is TSCl in presence of pyridine. Okay. So okay, let's start. So we'll begin with the first option. Okay. Option A. So what does it say? It says this is COOH, right? So this is it. Sorry, this is alcohol. Okay, wait a minute. Okay, so this is basically alcohol part. Okay, so the first step is in presence of pyridine. We know pyridine is a base, and we know tosyl chloride. Chloride is a good leaving group, and this converts it into OTS, that is tosylate. So you essentially get OTS here, just substitution by the tosylate. Okay. So in the next step, it says Ki, potassium iodide is added. Okay. So you know now it has been converted to a very good leaving group. So typically the I minus is going to attack here at this side. This will lead to the leaving of OTS group. That is the tosylate group, which is a very good leaving group. So that you get iodine here. Okay. And in the next step, it has been added magnesium in presence of ether, then carbon dioxide. Okay. So you know that whenever you have a substituted halide and you are providing magnesium in presence of an ether, so it gets converted to Grignard reagent. So this will get converted to a Grignard reagent. Okay. So this is a Grignard reagent now. So next, CO2. You know, this is negatively charged. It will be acting as a nucleophile now. So you will be getting this thing. Okay. This is in presence of H plus, that is acidifying the negative charge. Okay. So this is the final product. So you see, if we look at the final product here, it matches with the final product. So option A is one of the correct answer. So moving on to the next one, option B, same tosyl chloride has been added, but instead of Ki, they have added KCN, that is potassium cyanide, followed by the basic hydrolysis and HCl addition. So let's look at it, the second one. Okay, let's look at the second one as well. Okay, so basically, just a minute. Yeah, so let's look at it. So option B says first you are adding the same thing, Tosyl chloride in presence of a base. The sequence stays the same. That is your tosylate conversion. Followed by that, instead of Ki in the second case, you are adding KCN. Same sequence of reaction, just with a different nucleophile. So you are converting it into a cyanide, CN, the nitrile group. Then it says basic hydrolysis, aqueous solution of sodium hydroxide. So if you take a look at this, basically this is your cyanide group. So it attacks here, and then you take it up like this. You have acidified it. So this is like your NH group. This is your O negative. Okay. And then it undergoes tautomerism again. So what you get is basically the double bond, it has shifted the position. And what you get here is your amide. And if you further treat it with again OH minus, because it's mentioned concentrated NaOH, so this NH2 minus will be leaving, which will be forming ammonia as the byproduct, and you will be getting essentially an acid here. So basically an acidic salt, because it's sodium hydroxide, acidic salt. Okay. And finally, when they are adding HCl here, this acidic salt is converted to an acid here, right? So this is also the desired product that they are looking for. So even option B is correct as well. So two options A and B both are correct. Now we'll come to C, option C. Okay. So option C gives the Jones reagent. It's an overoxidant, we all know that. And followed by that, the Darzens reagent SOCl2, followed by your CH2N2 diazomethane. Okay, let's take a look at it. Just a minute. So I'm going to erase this part. Okay, so let's take a look at option C. So option C says at the first stage, what they're doing is basically they're treating it with the Jones reagent. Okay, this is the Jones reagent. Jones reagent. So it's an overoxidant, and you know that Jones reagent should directly convert it into an acid. Followed by that, SOCl2, it's a good chlorinating agent, popularly known as the Darzens reagent. So you convert it to acyl chloride. Okay. And followed by that, they are adding diazomethane. You know that in diazomethane, these type of reactions occur. This part basically acts as the negatively charged nucleophilic part. This thing leaves, and you get a substitution here. So basically it is like CH2 N2 positive. Okay. So followed by that, they are basically treating it with, another one. Okay. So basically you see, in order to remove this part, CH minus can also act as a like base. So this is CH negative and this is N2 positive. And you know that N2 positive will always want to be neutralized and removed in the form of nitrogen gas. So this goes like O minus. This is your N2 positive. So this bond comes here and this bond shifts here. So basically you get nitrogen gas as the byproduct here. It removes N2. Ultimately, the thing that you get here is double bond C, double bond O. Okay. Now this is your ketene intermediate. So this is your ketene intermediate. And in the next stage, what they are doing is basically they are treating it with Ag2O and H2O. That is nothing but uh, moisture, that is water, the attack of water on this electrophilic site. Okay. Okay, just a minute. Yeah, yeah. Okay, okay. So we missed out a carbon here. Okay. This was basically CH negative. Okay, yeah, yeah. We missed out a carbon here actually. No issues. Yep. We missed out a carbon actually. Okay. So basically after this stage, so what happens is we have another carbon here basically. CH negative is there. So this bond, once it shifts here, okay, this bond, this bond, so once it shifts here, right, you are going to actually get this N2 positive, and once it shifts back after this thing goes here, you get this, that is your this thing, double bond C, then double bond O. Okay, so you have one carbon here basically extra. Okay, so instead of this you make it right. So instead of this you just write this as double bond C, double bond C, double bond O, correct? Because one carbon is extra basically, nothing else. And then if you attack the water molecule here, then it can go here and this thing can just tautomerize. Okay, that is, this thing can just tautomerize here. So this is not a double bond. This is C, double bond C, double bond O. Okay, so essentially you get CH2 and COOH. Okay, same as the product you desired. So option C also gives you the desired product, correct? So this is also the correct answer, right? Option C is also correct. Option D, if you look at it carefully, it's directly the Jones reagent followed by CH2N2. So if you look at this, this is directly the Jones reagent followed by CH2N2, correct? So option D, if you look at this, you are having this. If you directly treat with Jones reagent, you will get the acid, no doubt. But this kind of rearrangement that you got here will not be occurring to give you the ketene intermediate. You will directly get an acid, and then when they are treating it with CH2N2, this will actually methylate this particular portion. It will act as a base because of the high acidity of this proton being next to an acid. So after this, you are going to get O minus along with CH3 and N2 positive after the proton abstraction. This is going to just attack here and you are going to get an ester linkage here. So this won't be the product. So your correct answers are A, B, C. That's it. Okay. Correct answers are A, B, and C. So you got A, B, and C as the correct answer. This is not the correct answer. Okay. This is not the correct answer. So yeah, that was a good question, and I hope you liked the video. Please subscribe to the channel for more. We'll be coming up with more MSQ and NAT questions. Thank you.